All right, let's kick off this explainer with a seriously mind-bending question. How exactly do you move a skyscraper? And actually, scratch that. I'm not talking about a normal, stationary office building. I mean a fully fueled, hyper-advanced piece of aerospace technology standing hundreds of feet tall, absolutely loaded with volatile propellants, and getting ready to head for the stars. I mean, it sounds like pure science fiction, right? But NASA does this on a regular basis.
So how do they pull it off?
Well, the answer is a massive crawling machine that tops out at a blistering, wait for it, 1 mile per hour when loaded. It is literally carrying the weight of America's space ambitions right there on its back. And this 1 mile per hour crawl, it isn't just a quirky fun fact. It's really the mechanical heartbeat of our entire journey to the moon. Because when you're moving something that mind-bogglingly massive and yet that incredibly delicate, every single inch matters. But hey, before we look up to the stars, we kind of need to look down at the ground first.
To truly wrap our heads around this cosmic transporter, it helps to look at its earthbound cousins first.
I'm talking about the machines designed to literally reshape the planet, redefining the absolute limits of size, power, and human ingenuity. Just to put the scale into perspective, think about the CAT 797F mining truck. It's an absolute beast of a modern machine, hitting 42 miles per hour while carrying a 400 short-ton payload. Or what about the legendary Big Muskie? This was a 22-story tall dragline excavator weighing 13,500 short tons. Its bucket was so gigantic, it could literally scoop up 2 Greyhound buses side by side. No joke. Over its lifetime in the Ohio coal mines, it moved twice the amount of earth as the entire construction of the Panama Canal. But then we get to NASA's crawler. It weighs in at a massive 2,721 tons. But it's engineered completely differently. It's not for aggressive digging. It's built for delicately balancing our most precious technological achievements.
Now, obviously, you don't just toss the keys to a multi-million-pound piece of hardware to just anyone who asks. Whether you're operating monuments of mining or infrastructure giants at the Hoover Dam, it requires strict, written safety qualifications. We are talking elite operators here. It takes rigorous training and absolute nerves of steel to command this kind of raw industrial power, especially when you know that even the tiniest miscalculation could end in absolute catastrophe. So let's zero in on the star of the show. Built way back in 1965 by the Marion Power Shovel Company, NASA's ultimate heavy lifter demands a truly staggering amount of energy. To give you an idea, Big Muskie used to consume as much electricity as a small city of 27,500 homes through this massive trailing cable. They often ran it at night just to save on the power bill. But the crawler? It uses a completely self-contained brute force power grid. Driven by massive diesel engines, it burns about 125.7 gallons of diesel for every single mile it travels. Let that sink in. And those engines aren't even directly turning the axles. They're actually generating immense electrical power and driving massive hydraulic pumps that allow the whole thing to steer, lift, and crawl. Its internal tanks have to hold 5,000 gallons just to guarantee it can inch that massive payload out to the launch pad without running dry. The really crucial takeaway here is that this behemoth weighs 6 million pounds. It rolls on 8 tracks, 2 on each corner. Obviously, if you put 6 million pounds on standard tires, the whole thing would just sink straight into the Florida swamp, right? So it uses these massive treads to distribute all that ground pressure. And here's where it gets absolutely wild. Each of those tracks is made up of 57 individual shoes, and every single one of those steel shoes weighs 2,200 pounds. That is basically the weight of a compact car, and there are over 450 of them constantly grinding against the earth. And over the decades, these machines have built quite the resume. The crews affectionately nicknamed the twin machines Hans and Franz, and they have quite literally carried the weight of history on their broad steel shoulders. If you trace their timeline back to 1965, you'll see these 2 crawlers have reliably hauled basically everything, from the Apollo Saturn V rockets that first took humanity to the moon, to the space shuttles that flew for 3 decades, all the way to today's Artemis missions. Instead of retiring them to a museum somewhere, NASA actually gave them a second life. They are seriously the unsung heroes of spaceflight, present for almost every single major American crewed spaceflight milestone. And get this,
Even though they creep along at just 1 mile per hour when fully loaded, Hans and Franz have logged over 3,400 miles on their custom river rock crawlerway over their lifetime. That is like driving from Miami to Seattle. The average trip from the vehicle assembly building out to Launch Complex 39 takes about 5 long hours, and the pathway they drive on, it's 7 feet deep, packed entirely with Alabama and Tennessee river rock. Now, you might be wondering, why river rock specifically? Well, it's not just about finding a hard surface. The rounded shape of the rock acts almost like millions of tiny ball bearings. They absorb the immense crushing weight of the crawler, distribute it evenly, and, this is super important, they prevent any sparks that could accidentally ignite escaping rocket fuel. Pretty genius, right? But honestly, even more impressive than the raw strength is the sheer precision of this thing. There's a specialized laser guidance system combined with active hydraulic leveling cylinders that keep the skyscraper-sized rocket within just 1 foot of perfectly level at its tip, even while it's climbing the 5% grade ramp up to the launch pad. It maintains a tolerance of just 10 minutes of arc. That is 0.16 degrees. Just imagine trying to balance a broom on your finger while walking up a hill. But the broom is a 300-foot-tall rocket packed with delicate electronics and high explosives. It takes a highly coordinated team of nearly 30 engineers, technicians, and drivers inside the crawler to pull off this delicate balancing act. As our goals in space evolved, so did the hardware. See, the payload started getting much denser, and the launch towers got significantly heavier. The historic hardware really needed a massive structural and mechanical update just to keep up. So, between 2012 and 2016, Crawler Transporter 2 underwent an epic transformation. We're talking massive new Alco diesel engines, totally modernized computer systems, beefed up brakes, and totally revamped hydraulics capable of bearing the extreme loads of modern deep space vehicles. This upgrade was absolutely essential. Why? Because its lift capacity had to jump from 5,400 tons to a mind-blowing 8,200 tons. It was explicitly engineered to handle the immense weight of the brand new space launch system. Achieving this supercrawler status meant it could now safely transport an 18 million pound payload. 18 million pounds. It's just such an incredible story of taking historic 1960s Apollo-era hardware and adapting it to meet the brutal demands of 21st century deep space exploration. And that brings us to where we are heading next. With the supercrawler fully forged and ready to go, we finally arrive at its ultimate purpose. All of this extreme engineering, all of this massive scale, it all points in one specific direction. Today, bathed in the glow of our futuristic lunar ambitions, this crawler is actively delivering the Artemis hardware that's going to establish a permanent human presence on the moon. We aren't just going back for a quick visit to plant some flags this time, we are going back to stay. We'll be using the lunar surface as a long-term laboratory, acting as a crucial stepping stone for future crewed missions to Mars. This 6 million pound relic from 1965 is quite literally enabling humanity's next great leap into the unknown. Well, I really hope you enjoyed this explainer. I just love the beautiful irony that humanity's fastest leaps into the deep cosmos rely entirely on a machine that drives slower than you can walk. Make sure to subscribe and definitely drop your thoughts down in the comments. I mean, if moving 18 million pounds to a launch pad takes this much raw, earth-shaking power, what kind of leviathans are we going to have to build when we finally set our sights on Mars? Let me know what you think, and I'll catch you on the next one.